Well, now we research about 145. Sense of measure zero. Assume throughout this section that X capital A mu is a measure space. A set of measure zero or none set is a measurable set N of capital A such that mu N is equal to zero. Let capital P be a name for some property that a point X of big X may have or not have, depending on X. For example, if f from X to 0 infinity is a measurable function on X, then capital P could stand for the condition fx is greater than 0, or for the condition fx equal to 0, or for the condition fx is equal to infinity. Or if fn from x to r is a sequence of measurable functions, the property capital P could stand for the statement the sequence fn x converges. In such a situation, we say that capital P holds almost everywhere if there exists a set n in X of measure 0 such that every element X of X minus n has the property capital P. It is not required that the set of all elements X of big X that has the property capital P is measurable, although that may often be the case. Example 1.46. Let Fn from X to R be any sequence of measurable functions. Then the set E is equal to the set of X. X is in X such that the sequence Fn X n from 1 to infinity is a Cauchy sequence. It is equal to the intersection of the union intersection of sets X is in X such that absolute value of Fn X minus Fmx is less than 1 over 2 power k is measurable. If n is equal to x minus e is a set of measurable 0, then fn converges almost everywhere to a function f from x to r. This function can be chosen measurable by defining fx is equal to lim n tends to infinity fn x for x is in e and fx equal to 0 for x of n. This pointwise limits of the sequence of measurable functions Gn is equal to Fn He, and hence is measurable by part 2 of theorem 1.24. The first observation is that every non-negative function with finite integral is almost everywhere finite. We have lemma 1.47. Let f from x to 0 infinity be a measurable function. If the integral on x, f d mu is less than infinity, then f is less than infinity almost everywhere. Proof. Define n is equal to the set of x. X is in x such that fx is equal to infinity. And h is equal to infinity of 3n. Then h is less than or equal to f, and so infinity mu n is equal to the integral on x. H d mu is less than or equal to the integral on x f d mu it is less than infinity by theorem 1.35. Hence, mu n is equal to 0. The second observation is that if two integrable or non-negative measurable functions agree almost everywhere, then the integrals agree over every measurable set. Lemma 1.48 assumes either that fg from x to 0 infinity are measurable functions that agree almost everywhere, or that fg from x to r are mu integrable functions that agree almost everywhere. Then the integral on a f d mu is equal to the integral on e g d mu for all a of capital A. The proof of this lemma is homework for everyone. Now we have the lemma 1.49. Assume that f from x to 0 infinity is measurable, or that f from x to r is mu integrable. Then the following are equivalent. I, f is equal to 0 almost everywhere. Double I statement. So integral on a f d mu is equal to 0 for all a of capital A. And the third statement, the integral on x, the absolute value of f d mu is equal to 0. Proof that the first statement implies the second statement is the content of lemma 1.48. That second statement implies the third statement is obvious in the non-negative case. In the integral case, define a plus is equal to the set of x in x such that fx is greater than or equal to 0. A minus is equal to the set of x in x such that fx is less than 0. Then f plus is equal to f a plus, and f minus is equal to minus f a minus by 1.24. Hence, we have this lies true by theorem 1.44 and the second statement. It remains to prove that the third statement implies the first statement. Let f from x to 0 infinity be a measurable function such that the integral on x f is equal to 0 and defines the measurable says an is equal to x of x, the set of x in x such that fx is greater than 1/2 power n for n in n. Then we have this line for all n in n by theorem 1.35. Hence, mu n is equal to 0 for all n in n. And so n is equal to the set of x in x such that fx is different from 0, and it is the set, the union of an and from 1 to infinity is a set of measure 0. In the integrable case, applies this argument to the function, the absolute value of f from x to 0 infinity. This problem lemma 1.49. And we have the lemma 1.50. Let's f be L1 E mu. Then the integral on x f g mu, absolute value of this is equal to the integral on x absolute value of f d mu if and only if f is equal to the absolute value of f almost everywhere, or f is equal to minus absolute value of f almost everywhere. The proof of lemma is homework for everyone.